Welcome, calculus students, to our very first video notes lesson for the 2021-2022 school year. We are going to be covering section 1.1 from your textbook, which is just giving you a preview of what calculus is for. So just to start off with some key terms, of course, calculus being the very first one. At the level we are in this course, this is Calculus AB. Calculus is going to be used, it's a branch of mathematics that is going to be used to answer two main questions. So these are the two main questions that really we're seeking to develop and fully be able to answer by the end of this school year. So the first one is, how do we find an instantaneous rate of change? The rate at which one variable is changing with respect to another at an instant. Not over a period of time, but like at one specific instant. So that's question number one, and we pretty much take all of first semester to fully develop that answer and then also look at some applications of finding instantaneous rates of change. The second question that calculus seeks to answer is, how can we find areas and volumes of strange looking shapes? So not your typical geometric shapes with straight edges or perfectly round circles, but stuff that kind of might be curvy on one end and straight on another, or just kind of a weird, not symmetrical curve type of shape. So that will be addressed during second semester. And the shocking and amazing part is that these two questions, which are seemingly very unrelated, like this one has to do with motion, right? Rates of change. This one has to do with just size and shape of things. But these two are actually completely related. And that's how we start second semester. So I'm not going to give it away yet. You'll have to hang in there to find out how those are related. Now, in our attempt to answer those two questions, we really have to kind of understand the difference between what a tangent line is and what a secant line is, because that will help us kind of break down the difference between what we consider to be an instantaneous rate of change versus an average rate of change, something that happens over a period of time. It all boils down to these two types of lines and then the slopes of those types of lines. So if you take a look at this image here, we've got one line that is said to be tangent to this curve, and then the red line that is secant to the curve. So a tangent line, the definition is a line that intersects a function at only one point. Now that has to do with the point of tangency. That's what we would call this thing right here. I'm going to zoom in on it. We call it a point of tangency because if you look right at that point, notice how the curve right there has a certain direction that it's moving right at this instant. We tend to think of one point, I'll just call this A, one point as an instant. And right at that instant, this tangent line is parallel to or copying that same direction. And then it just sort of extends it infinitely in both directions. But if you look right at that point on that curve, this tangent line is using the same direction. You could say that it's running parallel to or grazing or just kind of kissing the curve right at that one spot and then just taking that same direction and extending it. So that's what we mean by tangent line. It doesn't mean that the line won't ever intersect the curve at another point, because this curve could maybe extend that way, right? It might go down. And then if I continued my tangent line, that might hit the curve, right, in another point. So when we say that it intersects the function at only one point, it doesn't mean forever over the whole domain of that function. It just means at the point in question. At the point of tangency, it's only hitting the curve at that one point and then just kind of extending the direction of the curve infinitely. Whereas a secant line kind of has a different role. A secant line is purposefully taking 2 points on the curve. Maybe I'll say this is at point A and then this one's at point B. And it's purposefully just trying to connect them. It's kind of ignoring the direction of the curve and just taking 2 points on the curve and just connecting them with a straight line. That's kind of how we can think of a secant line, just connecting 2 points on a function, kind of ignoring the direction of the function. And you can see how it kind of hits the curve at an angle, right? It's not trying to run parallel to the curve like the tangent line was. It's just connecting 2 points on the curve. That's how we think of a secant line. Whereas a secant line is just looking at sort of an overall rate of change over a period of time, over an interval from A to B on a curve. It's just saying, okay, from here to here, how much did the function go up and over? What's the average rate of change from A to B? Versus the tangent line, which is only focused on point A, and just saying, what's the direction of the curve? What's the rise over run of the curve just at this one point? So that's the main distinction between the two. Now here in this image, you can see how there was, at the beginning of this, a secant line connecting point P to point Q. So again, you have this interval, and then we're just connecting those 2 points. And then you can see how it's taking that point Q and sort of sliding it down this curve and having it sort of approach P and eventually getting a tangent line at P. This is kind of the bridge, one could say, between finding a secant line and then using it to eventually arrive at the tangent line. We'll be kind of doing something similar to this at the end of this video. Let's take a look at example 1. So in example 1, you can see it's asking you to decide with each question posed whether you could solve it with pre-calculus techniques or whether calculus would be required. Now, when we say pre-calculus, we don't just mean the class you took last year. We mean any math that you took before calculus. So that could include everything even as far back as just simple arithmetic, maybe pre-algebra, the concepts you learned in that course, everything learned in Algebra 1 or 2, definitely some geometry, and some trigonometry. If a problem can be solved using any of these techniques, then we go ahead and just use those math skills. It's when I can't use the skills learned from these classes that I have to go further and use calculus. So that's what you're going to be deciding. Can I solve this with something I've learned before, or would I need something more? If you have to use calculus to solve it, obviously you can't do that yet, so we're going to ask you to simply just sort of estimate a solution using one of these other type of math skills. So let's look at the first part of example 1. It's asking us to find the distance traveled in 15 seconds of time by an object that's traveling at a constant velocity. So that's nice. That simplifies things quite a bit, of 20 feet per second. So if you look what we have here, we're being asked to find distance and we're given time and we're given a rate, right? That's what velocity is. It's a rate. It's feet per second. So back in pre-algebra, I believe, you learn a formula called distance equals rate times time. I believe in some classes they refer to this as DIRT. Distance is rate times time. This is the DIRT formula. This is just very basic, and since we have all the information we need and the velocity is a constant velocity, I can just multiply the 20 to the 15 to get my distance. So just using simple arithmetic and pre-algebra, I can see that this object traveled 300 feet in that 20 seconds of time, because it's covering 20 feet every second. For 15 seconds would be 300 feet. Just a quick comment on the units. So this 20 right here, this was in feet per second. This 15 right here was in seconds. You can think of that as like seconds over 1. So the seconds cancel out and the units you're left with are just feet. Okay, so part A did not need calculus. I was able to just use simple pre-algebra to solve it. Let's take a look at part B. So we have Rihanna riding her Segway on a path modeled by this function here, where x and f of x are both measured in miles. So my x-axis is representing miles, horizontal miles. My y-axis, or f of x axis, is representing miles as well, so probably vertical miles. So this is kind of helping us see her elevation as she travels horizontally. So this wants us to find the rate of change of elevation at the instant, right, which is 1 point, when x is 2. So it says see figure. Well, there's nothing here. We're going to have to create this ourselves. So we're just going to sketch a brief picture of this function here. First of all, I want you to notice that this is a quadratic function because my x is squared. It would be opening down because the coefficient in front of x squared is negative. So it's going to look something like this. It'll have an x-intercept at 0, 0, and then another one at 5, 0. So we'll plot those points. Go ahead and do that on your worksheet. And then it has what we call a maximum point at 2.5, comma 0.75. So that would be in between 2 and 3 and up just like right there, just before 1. And then it's going to open down. Okay, so there's a rough sketch of our picture, of our figure. And it wants us to find the rate of change of elevation at x equals 2. So right here, it just wants us to kind of figure out what's the slope of this curve. So if I were to draw a tangent line, something that's just sort of taking the direction of that curve and extending it, the rate of change would be the slope of that tangent line. So this is asking me to find the slope of the line tangent to the f of x curve at x equals 2. That would help me kind of figure out at this one point, at this instant, what's the rate of change? How much is it going up for how much it's going over? Well, I won't be able to find the slope of this line using pre-calculus. Calculus would be required. Well, so how do we find slope? The slope of a line we find by finding the change in the y values divided by the change in the x values. Or another formula from Algebra 1 was second y coordinate minus first y coordinate, y2 minus y1 over x2 minus x1. Second x coordinate minus the first x coordinate. So this slope formula, notice how it requires us to know 2 points. We have to know 2 points on this line, x1 and y1, x2 and y2, in order to be able to find the slope of that line. But because this line is only hitting the curve at 1 point, we only know that 1 point. That 1 point was at 2, comma, and then we'd have to figure out what the y coordinate is when x is 2. So I'm going to put 2, comma, f of 2, and then we'd figure that out using this equation. But since the function only hits the curve at that point, and I know it kind of, the way I drew it kind of makes it look like it's hitting it here, but it's not really, it's tangent. So it's kind of more like that. So it's only hitting the curve at that 1 point. It's not hitting the curve at any other point. So I can't use this equation to find another point on the line because the only point that's from the equation that's on the line is at x equals 2. And I'm just drawing this line, so I don't necessarily know exactly another point on it. This is the only exact point on the line that I can find, using pre-calculus anyway. So what that means is that calculus would be required to find this exact rate of change at the instant when x is 2. I can use algebra, I can use this slope formula to get an estimate. I can estimate what this rate of change would be at x equals 2. But if I wanted to get the exact answer, I would need to use some calculus, which we haven't learned yet. So we're going to go ahead and just estimate using algebra. So we do know for sure 1 point on this curve is when x is 2. So I can plug 2 into this equation here. And when I do that, I get 0.72. So I do for sure know that this is 1 point on the line because that's where the line is intersecting the curve. So that is definitely a point on the line. That's my x1, y1. And then maybe what I could do is just kind of look along this line and maybe pick another point, sort of estimate where that point is. This looks like it's at 4 and then maybe just a little bit higher than 1, but I'll just kind of say 4, 1. This is my estimate. The second point, this would be my x2, y2. Now that's not necessarily the exact point that this line goes through. In fact, without calculus, I'm unable to find the other points that this line goes through. But just using algebra and graphing skills that we've learned before, I can kind of estimate, right, that another point would be somewhere around 4, 1, and I can use that for my second point. And then I can use this slope formula here. So I'm going to do the second y minus the first y, so 1 minus 0.72 over 4 minus 2. And I get 0.28 over 2, and then that kind of simplifies down to 0.14. So I could say that the rate of change of elevation is roughly 0.14 or 14 vertical miles for every 100 horizontal miles, or 1.4 vertical miles for every 10 horizontal miles, however you want to think about this decimal. But that would be an estimate for my rate of change of elevation. Now, just a quick side note. I happened to calculate the exact rate of change earlier, And it turns out that the exact rate of change the rate of change of elevation at time x equals 2 is 0.12. So our estimate here, just from using pre-algebra, is actually not that far off. So that kind of also goes to show the power of the math you've learned before, right? Don't forget any of it because it's still quite useful. And then when it stops being useful or when it's not enough, that's why we are now learning calculus to help us go beyond to answer these questions here. How do we find an instant rate of change? How do we find a slope of a tangent line? There is an answer. It's coming. How about you try one? Why don't you go ahead and pause the video, try to answer these questions, and then come back to check your answer. So let's take a look at part A of this you try. So this is asking us to find the distance traveled. Okay, so we did that back in the first example. It gave us the time in 6 seconds by an object traveling at a velocity of, and then it gives us a function, v of t, so velocity at time t equals 20 plus 7 times cosine of t, feet per second. So this velocity is not constant, right? It's not just going at 20 feet per second like it was in example 1. In fact, at every different time t, this velocity is different. It's changing. So this is a type of situation where in order to find this distance traveled, I would definitely need calculus. But with a little bit of pre-algebra, I could get an estimate because I know this formula, distance equals rate times time, and I know my time was 6 seconds. What I could maybe do is find an average velocity over that 6-second period. I could find a few velocity values and take their average over those first 6 seconds. And again, there's lots of different ways you could do this. I just went ahead and used each second. I plugged this number into this equation. Make sure you're in radian mode. That's one thing you need to know for calculus, is that if you're using a trig function and you're plugging in, these values, we would need radian mode when we're plugging them in for t. Anyway, I plugged them in and I just got a few velocities. So here was the velocity at 1 second, 2 seconds, 3 seconds, etc. I got 6 different velocity values. Again, you could have used more if you wanted to. And then I just added them up and divided by 6. So I'm using sort of a basic average value formula. This is very basic, so I'm just getting an estimate, right? This is not going to give us the exact velocity, but it'll give me an estimate of, on average, what the velocity of this object was over this 6-second period. And then I do my rate times time. And again, the units were feet per second, and then the time was seconds, and then they cancel, and so I end up with feet. My answer is all the way over here, sorry, my estimate. So it approximately traveled about 118 feet over this 6-second period, estimating, right? I'd need calculus to figure out exactly, but this is my estimate. Now in part B of this you try, we see that JZ is riding his jet ski on a path modeled by this function, which doesn't make any sense in real life, but anyways, where x and f of x are measured in miles. So I've got miles on my horizontal axis and miles on my vertical axis. So this is a linear function, right? X is to the first power. So this line is just going to go straight up. So just like that. So it goes up 4.2 miles for every 1 mile that it goes to the right. And then up 4.2 miles for every 1 mile it goes up. So this would be like the jet ski is just like shooting straight up forever. But anyways, so calculus is not needed because this is a linear function which is straight. So the rate of change is constant, right? This is a constant rate of change. So it's very easy to know what it would be at 2, right? So that would be like right here. What's the constant rate of change? Well, it's just the same rate of change over this whole line. It's just going up 4.2 miles for every 1 mile, right? This number in front of x is your slope. Or if you wanted, you could take a couple points on the line. We can figure a lot of them out because we can just plug in different x's into the equation and then just use the slope formula from Algebra 1. So I just use this point and this point. So I could subtract those 2 y values and then subtract the 2 x values in the denominator. So change in y over change in x, and I get that same slope. So let's take a look at example 2. It's kind of asking you to do the same thing. Look at these different questions and decide whether or not you could find the exact answer using pre-calc or whether you'd have to go further and whether the problem would require calculus. If it does require calculus, we're going to go ahead and just try to estimate the solution using pre-calculus skills, all the math that came before calc. So look at part A. It's asking us to find the area of basically what looks like a rectangle. So that is a shape that we have an area formula for from geometry, and so no calculus would be needed. We would just use the area of a rectangle formula, which is base times height. I can tell from the coordinate here that this would have a base of 5, and then from the y coordinate there it would have a height of 2. So this would just have an area of 10 square units. So that was just using pre-calc. I didn't need, or geometry rather, I didn't need any calculus for that because all of the edges were straight. You come over here to part B though, and you can see this is what we mean by a strange shape. So the top of it's curved and like not even a constant curve. It's got all these little dips and grooves in it. So we would need calculus to be able to find the area underneath a curve that does that. Now this part's straight and this part's straight and that part's straight. It's the top that's kind of a little bit weird and curvy. So calculus would be required to find the exact area here. That's coming, by the way, in second semester. But we can still estimate it. We can kind of maybe cut this part off right here, and then we see that part's a rectangle, so we could find that area. So we could do sort of a rectangle area plus, and then we could maybe, let's see here. I could think of this maybe as like a trapezoid with the part here and here, and I could kind of think of it like that. So I can see it's not exact, right? There's some area there that I completely am missing out, and then there's extra area here that I'm including in this area of a trapezoid that some of it would cancel out, but not all of it. So I can see that this would not be exact, but it would be an approximation. So I'm going to do a rectangle area plus a trapezoid area. So I'm going to do a base times height is my rectangle area formula. And then the trapezoid area formula, this is from geometry. It's 1/2 base 1 plus base 2 times the height. So the base 1 would be this one. This would be my base 2 right there. And then this would be the height. Now for the rectangle, I can see it goes from -1 to 10. So that would have a base of 11. And then it goes from 0 to 5, so that would be a height of 5. So my rectangular area would be 55. My trapezoid area, my first base is 11. My second base goes from 3 to 10, so it's 7. And then my height goes from 5 to 8, so it's 3. So this would end up being half of 18 times 3, or 9 times 3, which is 27. So if I add the 27 to the 55 for my approximate area, I get 82 units squared. Okay, so for the U-try, you probably noticed that the top of this shape here originally was curvy, requiring calculus to get the exact area. We're not able to find the exact area of this without calculus. But using some geometric shapes, I just used a rectangle and a triangle, this guy right here and that guy right there, we could estimate it. It's going to be a little bit under because my triangle top would be straight and kind of miss out on some of that area there, but it would be somewhere around 30. I just did a base of 5 and a height of 4 for the rectangle, and then for the triangle it's half the base of 5 and the height of 4. Now over here though, in the part B, this was a graph of a line. It was linear, which has a straight edge. So I don't need calculus to find the area under that shape because it just makes the shape of a triangle. So I just did 1/2 base times height. It was a base of 4, a height of 8, and that got me 16 square units. Now we're going to conclude this video with example 3. And example 3 is really starting to walk us through the idea of a limit. Chapter 1 of this course is all on limits because limits are the foundational concept of calculus. They are the way that we go beyond pre-calculus and answer those two foundational questions of calculus. So we're going to be sort of working with a limit in a very visual sense. Okay. Also, we're going to be using the idea of secant lines and tangent lines in this problem. And you'll have a couple problems like this in your classwork, so I wanted to kind of show you what we're really after. Okay, so it asks us to consider this function here, which is the square root of x minus 1, and then the point 5, 2 on the graph of that function. Now see, eventually what we're going to do is try to estimate the slope of the tangent line, because without calculus we're not able to actually find the slope of the tangent line using some kind of formula, so we have to sort of at this level estimate it. So the way that we're going to do that is by first sketching the curve. So we're going to go ahead and sketch the graph of this. So I'm just going to use points, I'm just going to plug in a few points, and I'm going to use points that if I plug in a certain x would make it really easy for me to square root x minus 1. So I think I'll start by plugging in 1 because then I'd have the square root of 0, and that's easy. I can plug in 2 because then I'd have the square root of 1, which is 1. Then I think I'm going to jump to 5 because if I do 5 minus 1, I get the square root of 4, which is easy, 2, and then I'll jump to 10 because if I do 10 minus 1, I get 9, and then it's easy to square root 9. So I think I'm just going to use these points here, 1, 0, 2, 1, 5, 2, and 10, 3. So I like to refer to the shape of this graph as an eyebrow. In my opinion, the graph of a square root function looks kind of like an eyebrow. Anyway, here's the shape of our graph. Here is the point 5, 2. Now, if I were to draw a tangent line to the curve at 5, 2, so a tangent line kind of hits the curve at that point, kind of follows the direction of the curve at that one point, and then sort of extends it. So something kind of like that. Not a very steep line. And actually this eyebrow looks almost kind of flat. So it almost looks like the tangent line runs alongside it for quite a while there. So anyway, picture that slope in your mind, that rise over run, which is a very gradual slope. We're going to try to estimate the slope of that secant line. Now the way we're going to do that is by drawing 3 secant lines. One that passes through the point when x is 1, and then 3, and then 6. So the secant line that passes through the point at 1, 0, so it has to connect these 2 points. So it's connecting the point 5, 2 with the points on the curve at 1, 3, and 6. So remember at 1, that was the point 1, 0. So it's connecting those 2 points. So that would look something like this. So there's our secant line. We'll call that secant line number 1. And then they also want us to find the slope of the line that connects the point at 3. Now if I were to plug 3, I'd get 3 minus 1, I'd get 2 under the square root. So this would be the point at 3, square root 2. So that's right here, connecting that point at 5, 2. So that would look something like that. So you can see already it's getting less steep, right? As you move up this curve, the slope between the 2 points is going to get less and less steep. And then it wants us to pick a point on the right side over here at 6. Now if I were to plug 6 into this equation, I'd have 6 minus 1, which is 5. So that would be the point at 6, square root 5, which is right there, and then 5, 2. And then that line kind of goes like that, so it's even less steep than the line at 3, rad 2. So let me call the one in green, that'll be my second secant line. So this one will be secant 2. And then the one at x equals 6, that's secant 3. So you can see, as I move along this curve and eventually to the right of this point in question, which was at 5, 2, my secant slopes get less and less steep. So let's go ahead and find what they are. Let's find what the progression of these slopes is. So the slope of secant line number 1. So that would be the slope between these points, 1, 0, and 5, 2. So I'll subtract the y values, 2 minus 0. Subtract the x values, 5 minus 1. I get 2 over 4, or 1/2. Or 0.5 if you think of it as a decimal. So that's the slope of this line. So that's going to be our steepest slope, which is already not very steep, right? Going up 1 over 2, up 1 over 2. Not very steep. But I would expect that my secant slope of the second secant line would be even less steep. So that's the one where I have 3 comma rad 2, and then I'm passing through 5 comma 2. So I'm going to subtract those y values, 2 minus the square root of 2 over 5 minus 3. So that comes out to about 0.59 over 2, which is about 0.29. So you can see it is getting less steep, which I would expect. Now notice that these two slopes are on the left of the 0.5 comma 2. So I would imagine my slope of my tangent line at 5, 2 to be even less steep than those two, because it's just getting gradually less steep as you move from left to right. This function kind of gets flatter and flatter, or in the lines secant and tangent do as well. And then my secant slope of the third line, so that would be connecting the 0.6 comma rad 5 with 5 comma 2. So again, to find that slope, I'm going to do the y coordinates, but this time I'm going to subtract the other way since 6 comma rad 5 is on the right side. I'm going to do square root of 5 minus 2 over 6 minus 5. So you see that is about 0.24, so even less steep, right? So they gradually got less and less steep, and I imagine the slope of the secant is somewhere between that 0.9 and that 0.24. And that's what the last part of this problem wants us to do. It wants us to use the progression that we notice among these secant slopes to estimate the slope of the tangent line. So what are these trending towards? What would the limit of these slopes of secant lines be? Well, I don't know, somewhere between 0.29 and 0.24. So if I'm having to estimate, maybe I would guess somewhere around 0.27. I don't know, somewhere sort of between 0.29 and 0.24. So we could get maybe an estimate right around there. Well, turns out that the exact slope of the line, somewhere between the green and the purple, that slope is, the exact slope happens to be 0.25. So really close to the slope of this line that connects 0.52 and 6 comma rad 5. Very close. In fact, visually you can see they almost look the same. It's just a tad steeper, just a little bit steeper than that third secant line. And we will learn how to find these slopes eventually in Chapter 2, and it's a very efficient process. But to get there, we really have to establish this idea of a limit and what it means to tend toward something. So we're going to practice these problems in your classwork as well, and I'll see you there.